Today we will study about kinetic interpretation of temperature. The pressure of an ideal gas is equal to P barabar half 1 by 3 Nm V bar square. It can be written as P barabar 1 by 3 Nm V bar square, where V is the volume, V bar is the average velocity of the molecule. PV barabar 2 by 3 N गुना 1 by 2 m v bar square, where capital N is equal to a small n into volume equal to number of molecules in the sample. Internal energy E of an ideal gas is purely kinetic, so E barabar n गुना half m v bar square. Thus PV barabar 2 by 3 E. This is equation number 8. We are ready to interpret the kinetic interpretation of temperature. Now we know that PV by NT barabar kV, PV by NT barabar kV, where kV is the Boltzmann constant, so PV barabar NT kV. E barabar 3 by 2 NT kV. So E barabar 3 by 2 NT kV, or E by N barabar half m v bar square from equation A. So E by N barabar 3 by 2 kVT. Thus E is proportional to the absolute temperature of the gas. It is independent of P, V and natural nature of the ideal gas. This is a fundamental result relating temperature, a macroscopic measurable parameter of a gas, a thermodynamic variable as it is called, to a molecular quantity, namely the average kinetic energy of a molecule. Two domains are connected by Boltzmann constant. Thus we can say that the internal energy of an ideal gas depends only on temperature, not on pressure or volume. With this interpretation of temperature, kinetic theory of an ideal gas is completely consistent with the ideal gas equation and the various gas law based on it. For a mixture of non-reactive ideal gas, the total pressure gets contribution from each gas in the mixture. P barabar half a 1 by 3 N1 M1 V bar square plus N2 M2 V2 bar square plus dash dash. That is equation number 1. Now in equilibrium, the average kinetic energy of the molecules of different gases will be equal. That is half M1 V1 bar square half M2 V2 bar square barabar 3 by 2 kVT. So that P barabar N1 plus N2 plus dash dash kVT, which is Dalton's law of partial pressure. We get an idea of a typical speed of molecules in a gas. At temperature T barabar 300 K, the mean square speed of a molecule in nitrogen gas is M barabar Mn2 bata Na barabar 28 molecular weight of nitrogen bata Avogadro's number 6.02 guna 10 to the power 26 barabar 4.65 guna 10 to the power minus 26 kilogram. It is the weight of the nitrogen gas. Now V bar square barabar 3 kVT by M barabar 560 whole square meter square second minus 2. The square root of V bar square is known as root mean square speed or RMS speed and is denoted by VRMS. So VRMS for nitrogen gas is equal to 516 meter per second. It is the order of the speed of sound in air. So higher molecules have greater RMS speed. Law of equipartition of energy. The kinetic energy of a single molecule is ET barabar translational energy barabar half mvx square plus half mvy square plus half mvz square. That is equation number 1. For a gas in thermal equilibrium at temperature T, the average value of energy denoted by ET smaller than or greater is equal to E t power half mb x square plus half mb y square plus half mb z square is equal to 3/2 kVt. So this equation implies that half mb x square over half kVt, half mb y square over half kVt, and half mb z square over half kVt. Therefore, a molecule of free to move in a space needs 3 coordinates to specify its location. If it is constrained to move in a plane, it needs 2, and if it constrained to move along a line, it needs just 1 coordinate to locate it. This can be expressed in another way. We say that it has 1 degree of freedom for motion in line, 2 for motion in plane, and 3 for motion in space. Thus we can say that any molecule has to move in line for 1 dimension, in plane for 2 dimension, and a space for 3 dimension. Motion of a body as a whole from one point to another is called translation. Thus, a molecule free to move in a space has 3 translational degrees of freedom. Each translational degree of freedom contributes a term that contains a square of some variable of motion. It means half mvx square and similar terms in By and Bz. In equation A, we see that in thermal equilibrium, the average of each term is half kVt. Molecules of a monoatomic gas like argon have 1 translational degree of freedom. But what about a diatomic gas such as O2 or N2? A molecule of O2 has 3 translational degree of freedom. But in addition, it can also rotate about its center of mass, as shown in figure 1 for rotating axis 1, and for rotating axis 2 the rotation of molecule is shown. 2 independent axes of rotation of a diatomic molecule is shown in the figure. Figure 1 shows that the 2 independent axes of rotation 1 and 2 normal to the axis joining to the oxygen atom about which the molecule can rotate. The molecule thus has 2 rotational degrees of freedom, each of which contributes a term to the total energy consisting of translational energy Et and rotational energy Er. Thus, Et plus Er is equal to half mx square plus half mby square plus half mz square plus half I1 m1 square, I1 omega 1 square plus half I2 omega 2 square, where omega 1 omega 2 are the angular speed of about the axis 1 and 2, and I1 I2 are the corresponding moment of inertia of the molecule. We have assumed above that the O2 molecule is a rigid rotator. It means the molecule does not vibrate. This assumption is not always valid. Molecules like CO, even at moderate temperature, have a mode of vibration. It means its atom oscillate along the temperature, along the interatomic axis like a one-dimensional oscillator, and contribute a vibrational energy EV to the total energy. Thus, EV is equal to half mdy by dt whole square plus half ky square. So, E barabar Et plus Er plus EV. That is equation number 5, where K is force constant of oscillator, and by the vibrational coordinate, while each additional and rotational degree of freedom has contributed only 1 square time in equation 1, and 1 vibrational mode contribution 2 squared to normal kinetic and potential energy, a most elegant principle of equipartition, a most elegant principle of classical statistical mechanics states that energy A most elegant principle of classical statistic mechanics states that this is so for each mode of energy that is irrational, that is translational, rotational, and vibrational. It means to say that one is linear, second is rotational, and third is oscillational. That is an equilibrium. The total energy is equally distributed in all possible energy molecules, with each mode having as an energy equal to half kVt. This is known as the law of equipartition of energy. Now, for vibrational mode, it has both kinetic and potential energy. So, energy is equal to 2 गुना half kVt बराबर kVt for the vibrational case. Thus, molecule will rotate either in any axis have three mode of motion. First is translational, third is rotational, and second is rotational, and third is vibrational. Thus, the energy of translational, rotational, and vibrational can be combined in this way for rotating in a space for any molecule, either for liquid or for gas or for solid.